this might be the first time I feature on YouTube. Who knows where my career will go from here?
Yeah. You can become a famous YouTuber.
Right.
All right, so I'm very glad to welcome Petar Bakic from the University of Utah and announce his talk on how duality for exceptional theta correspondences. Now I will share the slides with you. Please, Petar.
Okay, well, thank you very much for the invitation and the introduction. I'm very happy to be here at Weizmann, at least virtually for now. As Dima said, today I'm going to talk about exceptional theta correspondences, and in particular, how duality for exceptional theta correspondences. And here's a little preview of the contents of this talk. First, in the introduction, we will talk about the classical theta correspondence, explain what it is and how it comes about. After that, we will explain how an analogous construction arises in the exceptional setting. And finally, we will talk about how one may go about proving a how duality type result in this exceptional setting. So to begin with the talk, well, before we actually begin, just a few preliminary remarks. Throughout the talk, F will be a non-Archimedean local field of characteristic 0. The groups we consider will be F points of algebraic groups. And when we talk about representations, we talk about complex admissible representations of these groups. So what is theta correspondence? Here we're talking about the local version of theta correspondence. And to set up the classical theta correspondence, one actually needs two key ingredients, one of which is the Weil representation, which we denote by lowercase omega, of the metaplectic group. Now, the metaplectic group is a double cover of the classical symplectic group, and its significance is precisely the fact that on it we have this Weil representation. Once we have the Weil representation, the other ingredient we need is the so-called dual pair. We will say that G and G prime form a dual pair inside this symplectic or the metaplectic group if those are reductive groups and one is the centralizer of the other. So as soon as we have this type of situation, what we can do, of course, is we can restrict omega to this G times G prime, this dual pair sitting inside the metaplectic group. And then a very standard representation theoretic question would be to describe this restriction. So how does this restriction decompose? In more detail, how we do that is, so we have this dual pair G and G prime. If we fix an irreducible representation, say of G, then we can look at the maximum isotypic quotient of omega with respect to that representation. So we're looking at the maximum pi isotypic quotient, and this is of the form pi tensor theta of pi. For some, it turns out to be admissible representation of G prime. And then the question is, we want to know as much as we can about this representation theta of pi, which we call the big theta lift of pi. And here really the crucial result and actually the starting point of the theory of theta correspondence is the Howe duality theorem, which says the following. First, theta of p could be 0, right? If pi is not a quotient of the Weil representation, then theta of pi is just taken to be 0. But if it's non-zero, so if pi appears as a quotient, then it is an admissible representation of finite length. So we have some control of the size. Furthermore, if theta of pi is non-zero, then it has a unique irreducible quotient, which we call the small theta lift and denote by lowercase theta of pi. And there is this injectivity property. So if two representations lift to the same thing, if they have same isomorphic theta lifts, then it turns out the original representations have to be isomorphic. So what this result does is really it sets up a correspondence between, on the one hand, representations of G, and on the other hand, representations of G prime. Of course, you can go in the other direction as well. You can start with a representation of G prime and do the same construction. And this is what we call theta correspondence.
Does one need any stable range assumptions for this?
No. So this is a general fact that's for classical groups been proven in full generality.
Thank you.
Oh, by the way, I should say, at any point, if you have questions, please feel free to ask. Also, I will be looking at the chat from time to time, so you can also type the questions and comments there. So looking forward to any questions. So this sets up a correspondence, and it turns out that this correspondence is extremely useful. There's all kinds of reasons why one would study such a correspondence. It has, so of course, this has a global version as well. And this global version is a really useful tool within the theory of automorphic forms or what we call the Langlands program nowadays. So it's been used to prove certain instances of Langlands punctoriality, but also in just the local setting, it's a very widely used tool in terms of local representation theory. So just a very well studied and very useful tool within the theory of automorphic representations and automorphic forms. And of course, when one knows this, one would like to have this theory extended to other settings. What we're looking for is now, the question is whether we can extend this construction to similar things in other groups. Of course, we saw that we need two ingredients. First, we need dual pairs, and that is something that's not too restrictive. I mean, dual pairs are a very general thing, and they appear almost in every reductive group. So really, the harder question is, can we find a suitable replacement for the Weil representation in the exceptional setting? And so this is what the first part of the talk is going to be about. We're going to describe how dual pairs arise in exceptional groups, and how we can replace the Weil representation. All right, so first, a couple things about the dual pairs. One thing that's remarkable about these exceptional groups is that even though they are truly exceptional, a lot of constructions, a number of constructions, and we do here is in a certain sense uniform. And so is even the construction of the groups themselves and the dual pairs that we study in them. All of those things start from the so-called Jordanalgebras. And Jordanalgebra is a non-associative algebra over our field, which satisfies these two axioms. The first is just saying that the algebra is commutative. The second is the Jordan identity, which in itself does not tell you much. But truly, the meaning sort of the second thing is that it implies that the powers, and even though the algebra is non-associative, it implies that the powers are well defined. So we say that the algebra is power associative. And what this enables us to do is, this is just purely abstract algebra, but this enables us to define sort of a generic minimal polynomial of an element in this algebra. And we will be interested in the so-called Freudenthal Jordanalgebras, where this minimal polynomial has degree 3. This is roughly speaking the algebras we are concerned with. Still very abstract in terms of the definition, so maybe it's good to look at an example. And it's actually easy to come by examples of Jordan algebras. You take any associative algebra, so any nice algebra you like, and it becomes a Jordan algebra as soon as you tweak the multiplication a bit. So this circle now denotes the new multiplication. And if you define the circle multiplication like this, you get a Jordan algebra. So if you would like to think about an example, you can think about maybe 3x3 matrices with entries in F. So are the regular matrix algebra, except with this multiplication here. So these are the Jordan algebras we are working with, and let's see how we get dual pairs and exceptional groups in the first place. What we will construct is a dual pair type G2 times the automorphism group of the Jordan algebra. Here's how we can do it. It is actually easier to explain the construction on the level of Lie algebras. And we were saying that there's this thing, so since there are powers, there is a minimal polynomial. And so the constant term of the minimal polynomial really is a determinant. When we look at Freudenthal Jordanalgebras, this determinant is, or a norm, if you like, is sort of a cubic form on this Jordan algebra. And so this Jordan algebra automatically comes with some sort of norm, or we call it determinant. In the example I mentioned of 3 by 3 matrices, this determinant is just the usual determinant of a matrix. What we then look at is the group of all F linear transformations that preserve this determinant up to scaling. So this is a certain group. And we can look at, since we're working at the level of Lie algebras, we look at its Lie algebra. It turns out that then we can, with these ingredients, we can define a Lie algebra structure on this space we denote H. So we have one copy of just the usual SL3, the Lie algebra L we just defined, and then we add these two pieces. W is the standard representation of SL3, J is our Jordan algebra, so we add their tensor product and its dual. And on this, it turns out we can define a Lie bracket. Well, SL3 and L are orthogonal. We already have the action of SL3 on W, that's the standard action. We have the action of L on J. And so it turns out we only need to sort of extend, and this gives us the Lie bracket, and it turns out we only need to extend this Lie bracket, which is non-trivial, but it can be done. We can extend it to this part we added, the standard representation tensor J and the dual. And once we do that, we get this big Lie algebra we call H, and it turns out this is a simple Lie algebra of one of the exceptional types. And how do we get a dual pair in it? Well, if we fix, I say here, a generic element, that just means an element E, which has a non-zero determinant. We take such an element and define G prime to be the centralizer of that element in L. So in this algebra here, in this piece here, we take the centralizer of such an element. And then we take G to be the centralizer of the G prime we have just defined. Then it turns out, and this just comes out of the Lie bracket with some computation, that G is a simple Lie algebra of type G2. So it has these three pieces, and this is isomorphic to a G2 type Lie algebra. And you get the dual pair condition automatically. So G is the centralizer of G prime, and which we have just defined. It turns out that G prime is also a centralizer of G. And that way we get a dual pair of G and G prime within H, or on the level of groups, when you bring that to the level of groups, that is a dual pair G times G prime in a bigger group, bigger exceptional group H. So this is a very quick, a very brief explanation of how to get these exceptional groups and dual pairs. Maybe it pays to look at a more concrete example. And here's one example we have already sort of mentioned. And this is one of these exceptional groups. The E6 exceptional groups corresponds to the Jordan algebra we mentioned. These are just 3 by 3 matrices with entries in F. We said that we look at the operators which preserve the determinant up to scaling. In this case, this is 2 copies of GL3 acting in this way. One of them acts from the left, the other acts from the right. Of course, the determinant of AXB inverse is the determinant of AB inverse times the determinant of X. So there's the scalar factor, and this of course, we quotient out by the center. The central copy of F embedded diagonally acts trivially, so we can quotient out the center. And this is the group which preserves the determinant up to scaling. So how do we get G prime? We fix an element. In this case, the easiest is to just fix the identity matrix. And then G prime is the elements which fix I. What does it mean to fix I? It means that A times the identity times B inverse is the identity. Or in other words, A times B inverse is the identity. That means that really A equals B. So we have a GL3 embedded diagonally into this group L. And of course, we have quotiented out the center. So we end up with the group PGL3. And that is how we get a dual pair G times PGL, G2 times PGL3. And in this case, the big Lie algebra or the big Lie group that we get from this J is the E6 adjoint split group. Here's Dinkin diagram of the E6. What's kind of cool to look at is this construction is sort of reflected in the Dinkin diagram. So let's see how that would work. You start from the Dinkin diagram of the big Lie algebra you're looking at, E6. And what you do then is you extend it. Here, I've taken the same diagram and I have added the negative of the highest root. This is the so-called extended Dinkin diagram. And now we have certain things that we want to consider in this diagram. First of all, the big algebra that we're starting from is type E6. And now I will do some surgery on this diagram and see how things that we want to study, how they show up. First of all, what I can do is I can cross out the vertex adjacent to the one that we have just added. In this way, I get what remains is this part here. We call this M, and this is just something of type A5. So I'm going to write A5 over here in M. Okay, so we're getting M is A5. What we can do then is we can cross out the vertex that is next to the one we have just looked at. So in this case, that would be the branch vertex alpha 4. Crossing out this next one does the following thing. It leaves us one copy of SL3, which is this A2 diagram over here. And it leaves us the rest of the diagram, which in this case we call L. And this L, in our case, consists of two pieces. Both of these two pieces are of type A2. So what I will do is I will say L equals A2 times A2. And the way we get G prime here, the one component of the dual pair, is you can see it from L by simply folding the pieces of L together. I have A2 and A2. When I fold them together, I will just get another copy of A2. So this A2 that we got corresponds to the PGL3 that we considered a moment ago. So somehow you can see these things that we deal with, and of course M and L has already appeared in our construction. Here it is. We needed it to construct H. M will also appear. As you can see, M is just a Levy factor of a certain parabolic in this Lie algebra H. Let's maybe look at another example, E7. It's pretty much the same thing. So now that I take the extended E7 diagram, I get this. What happens here is a similar, or actually completely analogous construction. first we cross out the vertex that's next to the one we added. What remains is this diagram here, which is D6. So M in this case is D6. And then we can continue our construction saying, well, the next step is to erase the vertex that was next to the one we just considered. In this case, this is alpha 3. Once again, we get a copy of SL3. And this other part that we call L, which is in this case just A5. So we have the A5 diagram here. And okay, this is maybe a little ambiguous, but sort of folding it, we get a dual pair C3. So in this case, in E7, you will get a dual pair that's a G2 times roughly the symplectic group SP6. Not really, but it's going to be PG SP6 really in this case. And this can sort of be done for any of these exceptional Lie algebras or Lie groups. And one interesting thing that is definitely worth mentioning is that if you do that for the Freudenthal Jordanalgebras that we consider, you get this this square diagram. So what are the Jordanalgebras? The simplest one we look at is just the 3x3 Hermitian matrices. That gives us the Lie algebra F4. We have looked at two examples, E6 and E7. In E6, the Jordan algebra is just the 3x3 matrices. In E7, the Jordan algebra is, well, these are symplectic forms on, or they do not need to be degenerate, but we can think of them as, it's just the exterior product, so we can think of them as the anti-symmetric 6x6 matrices in F6, and with entries in F. And the final Jordan algebra is sort of the Hermitian 3x3 matrices with entries in the octonions. These four algebras give us the four exceptional groups F4, E6, E7, and E8. And if for each of them we do the construction we just sketched using Dinkin diagrams, so we define these H, M, L, and G prime. What's remarkable is that we get this so-called Freudenthal's magic square. What's magic about this square is that it is symmetric. So we have E7, E7, E6, E6, F4, F4, and these things as well, A5, A5, C3, and A2, A2. So it is completely symmetric, even though the construction is not symmetric in any way. So that's why it's called a magic square. And it sort of shows how all of these things that we consider here do arise in a uniform fashion, even though we're dealing with exceptional groups here. In our case, we will, so in the rest of this talk, we will focus on one particular dual pair, and that's GU times the unitary group or the projective unitary group. And we get that dual pair in precisely the same manner, except we're no longer working with split groups. Here, K will denote a quadratic extension of F. And then the Jordan algebra we consider is the Hermitian matrices with entries in K. And we have the similar or the completely analogous construction GL3 with entries in K acts on J. And if we fix a generic element, so when the one where determinant is non-zero, in this case, it's convenient to take this one. But the subgroup fixing this element turns out to be the projective unitary group. And so we get the G2 times the projective unitary group in 3 variables. The big Lie algebra where this dual pair occurs is again of type E6, but it's no longer split. It's quasi-split E6 with a relative rank 4. So here's its Dinkin diagram. So this is the dual pair we will consider in this talk. This is the dual pair for which we consider our exceptional theta correspondence. Of course, these are just dual pairs. I haven't yet explained the other key ingredient, and that is the minimal representation. So if you remember, the question was, how can we replace the Weil representation in this exceptional setting? And the answer is truly that it can be replaced. There is a suitable replacement, and it's called the minimal representation. So let's see what it is. It turns out that there are multiple possible definitions, and the following is perhaps the easiest to state, maybe the most elegant. So say we have a representation pi of H. H you can think of as one of the exceptional groups that we just considered. Well, we can always consider its character distribution, and then by a standard representation theory result of Harish-Chandra, this distribution can be written as a sum over the nilpotent coadjoint orbits. So these O's are nilpotent orbits. The COs are just certain coefficients, and mu is an H invariant measure on each of those orbits. We take its Fourier transform, and this is how we can write the character distribution. Now, under certain technical conditions, we have a unique minimal orbit among these. So of course, if in the algebraic closure, we have the unique minimum orbit, but here we need to have certain technical conditions to have a minimal non-trivial orbit, of course. And then the definition is the following. We will say that a representation is minimal if its character distribution is supported only on the trivial and the minimal orbit. The support of this character distribution is called the wavefront set of this representation. So this can be rephrased as the representation is minimal if its wavefront set is consists only of the minimal and the trivial, orbit. And once you have this minimal representation, you can consider the same construction we considered in the classical case. So you have a minimal representation of H, and you have a dual pair in H, and you can restrict this minimal representation to the dual pair in question. So for us, H is the quasi-split E6, G and G prime are G2 and the unitary group. And when we restrict pi, we get, we can look at the same construction. We can look at maximum pi isotypic quotients of the minimal representation, and they are of this form, pi times theta of pi. The fact that capital letter pi, so the minimal representation, the fact that it's minimal really allows us to get a handle on this representation theta of pi. The minimality, as a consequence, has the fact that this theta of pi is not too large. We can control it. It will turn out to be finite, of finite length. But so again, here's the result we want to state. This somehow looks like the beginning of theta correspondence, but if we really want to have a correspondence, then Howe duality is something that we would like to prove. Once again, what is Howe duality? Here's the theorem we're trying to state. We're stating it here, and we're trying to prove it in our setting. So pi is a representation of G2, and we want to prove that the theta lift is either 0 or has finite length. We want to prove that it has a unique irreducible quotient when it is non-zero. And we want to prove this injectivity result, so that if we have isomorphic lifts, then they have to come from isomorphic representations. But this is the theorem we're after. And the strategy of proving this theorem involves sort of two, again, key approaches. The main idea is first to describe the Jacquet modules of the minimal representation. And this is a very old idea. I mean, if you want to study induced representations, then at some point you will have to use Frobenius reciprocity. And that really tells you that you have to know the Jacquet modules of the minimal representation. And the second idea, a much newer idea developed by Gordan Savin and Wojtek Gan, is the so-called period ping pong that we will discuss shortly. And this is really what enables us to get a hold on this exceptional Howe duality. So before we explain these two steps, maybe it's a good time to stop for questions if there are any. Okay, at any rate, what we have now is we have this minimal representation, which replaces the Weil representations. We have sort of briefly sketched how to obtain dual pairs in exceptional groups, and the construction is the same. We restrict the minimal representation to a dual pair, and now we want to have this Howe duality result. So first, let's look at Jacquet modules. Since this is an older idea, I maybe will not spend as much time discussing this, but so if you have studied the classical theta correspondence, then you have probably encountered or surely encountered Kudla's filtration, which is really a very important early result in the theory of theta correspondence, which really is a description of the Jacquet modules with respect to of the Weil representation with respect to the maximal parabolics. And this is an indispensable piece of the theory that we use almost all the time. So we would like to have the same type of thing here. First, let's look at the maximum parabolics that we considered here. There are three of them that we consider. And I will try to draw each of them on the Dynkin diagram. First is, the first one is the so-called three-step parabolic. I will explain the name in a moment, which is obtained by removing this vertex in the diagram, or so the relative diagram of this quasi-split A6 is an F4 diagram, and in the relative diagram that corresponds to this vertex. So you get a maximal parabolic this way, and maybe before we go into detail, just what it does is it's interesting to look at how it intersects our dual pair. It turns out that the unitary group survives, but the intersection with G2 actually gives us a maximum parabolic in G2. And so G2, as a rank 2 group, has two maximum parabolics. Both of them, this is what we call, we call them Q1 and Q2. Both of them have a Levy factor GL2. So this L1 is the Levy factor of one of the maximum parabolics in G2 is really isomorphic to a GL2. So this is a three-step parabolic. Then we have the so-called Heisenberg parabolic, which corresponds to this vertex alpha 2, or in the relative diagram, we have it here. Again, it intersects the dual pair in this maximum parabolic of G2. This is the other maximum parabolic. Again, we will explain the name Heisenberg in a moment. And sort of the last parabolic we consider is, well, I don't have a fancy name for that one. This one is just, let's call it maybe D4 parabolic. What it corresponds to is, I would like to remove this, but of course it's in the same Galois orbit, so I have to sort of remove these two if I want to have a parabolic defined over F. And what remains is D4, so hence D4 parabolic. And the relative Dynkin diagram, it's even simpler to see it. It's this B3 type diagram that remains. And unlike the previous two, this one, when you intersect it with the dual pair, G2 survives, and it intersects the unitary group in the Borel subgroup of the unitary. And you can think of Borel as just the upper triangular matrices and within the unitary group. So these are the parabolics we're considering. And ultimately we need Jacquet modules with respect to all three of these parabolics. But maybe let's just look at one of them to briefly sketch what is going on. First, a little bit about the structure of these parabolics. Looking at this three-step parabolic, maybe I can skip the details as to how we get it. But the reason it's called the three-step parabolic is that it's the unipotent part of the parabolic group the unipotent radical is a three-step nilpotent group. So that's why we call this a three-step parabolic. And on the level of Lie algebras, again, it is easy to see this. It has these three pieces: the bottom piece, middle piece, and the top piece, H1. So instead of the way we do this, the way we find these pieces is simply if we know the Lie bracket on H, which we know, simply compute that. So this is very prosaic work, but it can be done. Maybe just look at the dimensions or what each of these pieces contains. The bottom piece is a subset of this SL3. It just contains two copies of the field itself. Then the middle piece, I didn't say what E1, E2, and E3 were. E1, E2, and E3 are the standard basis of the three-dimensional space W, and E1, E2, E3 star are the dual basis. So the middle piece contains this dual of our Jordan algebra, and this is another technical detail. The dual can be identified with the Jordan algebra itself. There is a trace pairing, and you can identify J and J star. So really, we can think of this middle piece as just one copy of J. And the top piece has actually, since we have E1, E2, has two copies of J. So this is not particularly interesting if I just throw these facts at you. The reason I'm pointing out these facts is that we can see this from the Dinkin diagram as well. How we see this is, it turns out that H, so we have this SL3 copy in H here, and if you look at the maximal Curton in SL3 and look at the adjoint action on H, then it turns out that we have a root space decomposition, and that root system we get is of type G2. So we get a G2 type root system, but the long root spaces are one-dimensional. However, the short root spaces are, in this case, 9-dimensional, and they're isomorphic. Each of the short root spaces is actually isomorphic to J, the algebra we're starting from. So it turns out that you can see this filtration of the unipotent or the nilpotent part in the algebra language from this Dinkin diagram. And here I would like to illustrate that by saying, well, here's what we have. If we want to look at the three-step parabolic, we look at the direction of the short root and look at the three levels we have. First, the first level sort of has only these two long roots, and that's the bottom piece. And we see that it only has two copies of the field. The long root is just one dimension. Then the middle has one short root, and that is just a copy of J. And finally, the top part has two copies of J. So this situation corresponds exactly to what we have here. The bottom piece has two copies of F, the middle has one copy of J, and the top has two copies of J. And you can see this for the other parabolic subgroup we defined as well, the one we called the Heisenberg group. If you start in the direction of the long root, well, here we have, in the direction of the long root, the bottom piece has only this, so the center will be one-dimensional, and the rest of it, so here we only have two levels. We have two long roots and two short roots. So it turns out that the unipotent part in the other parabolic only has two level. It's a two-step nilpotent group, or in other words, it's a Heisenberg group, so that's why we call it a Heisenberg parabolic. So again, this is just a rough sketch of what happens here, but it's nice to see that all of these things do show up on the Dinkin diagrams. All right, but so far we haven't said anything about the actual Jacquet modules. These are just the parabolics and what they look like. Of course, one has to know a little bit about the structure of these exceptional groups. But the Jacquet modules, I'm skipping the computation, which is not trivial, but it is also something that has been done before, except maybe not in this particular case. For example, with respect to this three-step parabolic, since it's roughly speaking, it has 3 steps, the filtration of the Jacquet module will have 3 levels. That is roughly what happens. And it turns out that we have a nice description of these of this filtration. Just like in the classical Kudlas filtration, if you're familiar with that, the bottom pieces are somehow induced from smaller representations. This bottom piece is actually quite interesting because it's induced from a tinier version of the Weil representation. So it's somehow, when dealing with these filtrations, you also have to consider a small version of a classical theta correspondence. So it's kind of interesting to see all of what happens here. But this is just a statement of the result to maybe give you a flavor of what these Jacquet modules look like in this case. All of these groups we're working with are, unlike classical groups, I mean, there's a trade-off. These are exceptional, so they're kind of harder to understand. But then the Jacquet modules they all have small ranks, so they're relatively easy to describe. And once we have this, we already get a lot of control over our theta correspondence. So let's just maybe go over what we can prove using these Jacquet modules. Naturally, we use them to study theta lifts of induced representations. In particular, we can look at non-tempered pi, a representation of G2. And we actually get everything we need for Howe duality for non-tempered pi. We get the finite length of the theta lift. We get the uniqueness of quotient, and we get the explicit description of the theta lift. So it turns out we can get Howe duality for non-tempered representations just by looking at the Jacquet modules. And of course, you can do it the same in the opposite direction. Start from a representation of the unitary group and then consider the lifts to G2. The same thing happens here. So we can get all the information we need for non-tempered pi. We can get even a bit further. We can obtain this very nice bit of qualitative information, assuming that pi and sigma appear as a quotient of the minimal representation. And we see that it turns out that tempered has to correspond to tempered. So we cannot have one tempered and one non-tempered representation be a quotient of the minimal representation. So once we prove that this is a correspondence, we will know that this correspondence sends tempered to tempered representations, non-tempered to non-tempered. But this fact will also be important in the rest of the proof. So it gives us a handle on tempered representations as well. In addition to that, one important technical part is that we can say something about the theta lift of tempered representations as well. If I have a tempered representation, I can decompose its theta lift in the cuspidal and the non-cuspidal part. And of course, this non-cuspidal part can be analyzed using Jacquet modules. And it turns out that this non-cuspidal part has finite length. So if I want to prove the finiteness of the theta lift for tempered representation, really I need to study this just this cuspidal part if we want the finite length representation. And this is where this other key idea comes into play. This is the period ping pong that we want to consider. So as I mentioned earlier, a period ping pong is a relatively recent idea that was used by Gunn and Gordan Savin in an analysis of a different theta correspondence, also in the exceptional case. Here's what we need in our case. So we need certain groups we haven't mentioned before. First, we will be considering just ordinary generic representations of G2. Generic representations here arise much in the same way as in classical groups. So you take the Borel of G2, of course, you can get it by intersecting the two maximum parabolics that we have. And you take a Whittaker functional of the unipotent radical of V. And you can, what we're interested here is we're interested in the co-invariance of the minimal representation, but twisted co-invariance. So the twisted Jacquet module with respect to V. And it turns out that the psi twisted Jacquet module, the twisted co-invariance, is compactly induced from the so-called from a character of the so-called Shalaika group. So we need to explain where this comes from and what this Shalaika group really is. Where this comes from, this is actually maybe the easier bit. We have just computed the usual covariance. So this is a same type of computation. We are still computing some covariance, except these are twisted. So this goes back to an older work of Savin and Marty Weissman, and this is just a general result we have in this exceptional setting. What is this Shalaika group in our case? To define it, we need to look at the Borel, this time in G prime in the unitary group. So we mentioned earlier, Borel can be considered just as the upper triangular matrices, and the description of the unipotent radical, we have it here. So we see then when we quotient out the center, which is represented by this part, when we quotient out the center, the only thing that remains is this one copy of the field K. And that's why you can define a character on the unipotent radical just by letting it be psi composed with trace. And the Shalaika group is just the unipotent radical, a semi-direct product with the stabilizer of this character. And you can extend the character, this character, psi u prime, to the Shalaika group, and that's what we call pi s. So that's how you get, this is the Shalaika group. This is what we need to, this is what we're inducing from to get these covariants. Well, this Shalaika group appears because we study these Whittaker covariants, so to say. But we also need one key bit of information about the Shalaika invariants themselves. And this is again, one fact that we get is a multiplicity 1 type result, that when we look at the Shalaika this time, we look at Shalaika twisted covariants. The Howe space is one-dimensional for generic representations pi. And this is again obtained by an analysis of the structure of this space of covariants, which in turn needs another, the so-called Fourier-Jacobi groups, and that maybe extends, that maybe is out of the scope of this talk. But again, this is just an analysis of the covariant that gives us this result. And sort of equipped with these two results, the description of these covariants and this multiplicity 1 result, we can go into the so-called ping pong game. Now, here's why we call it ping pong. This is the result. If I have two representations, one of G and one of G prime, which whose tensor product appears as a quotient of the minimal representation, then I have the following series of inclusions and isomorphisms. These Howe spaces are called periods. And the reason we call it ping pong is, well, here you see you start from a period in G. V is the unipotent radical of the Borel in G. And then you send it to a period that happens in G prime. Shalaika group is a subgroup of G prime. And then you send it back to G. So I guess this game of ping pong is it's a relatively short rally. It only has serve and return. But in between, you get these three Howe spaces that are really interesting for our Howe duality results. And this result will be crucial. One thing to note is that part of this result is that if pi is a generic representation, then all of these spaces have to be one-dimensional. So this is what enables us to get a hold on this Howe duality, and we will explain how we do that in a moment. Let me maybe just say a couple words about how we prove this result. It's not hard to prove all these inclusions. 1, 3, and 4 are just pretty much the usual technical abstract manipulations of the Howe spaces. 2 is probably the most interesting step, so let's see how 2 happens. So we need to prove that the Hahn space, the Whittaker period is sort of isomorphic to this Shalaika period. Let's see how we would prove that. This Whittaker period here is, well, it's written as a Hahn space of V, but we can also write it as this Hahn space of V times G prime. Here's the minimal representation. On the one hand, well, we need V to be acting by psi V. And on the other hand, G prime, I have tau here because that's how theta of tau appears. So these two are isomorphic just by the construction of capital theta of tau. Now, once we have this, you can write it, well, you can write the same thing in multiple ways. This can be written as just the G prime Hahn space of the psi twisted coinvariance of the minimal representation and tau. This is just a general way to rewrite this thing. But now, if you remember what this is, we computed the Whittaker coinvariance, and we saw that these are induced from the Shalaika group, right? So this is induced from the Shalaika group, which tells us that we have this situation. And now, of course, you just use Frobenius reciprocity. The right adjoint of compact induction is a restriction. And you get this Shalaika period. This space here is in a standard way isomorphic to the one we need. So this is just general abstract nonsense. S. And so this is how we get the relation number 2. This is probably, as I said, the most interesting step. What pays to it pays to look at the other part of the result, which says that we have dimension 1 in case that pi is generic. Well, if pi is generic, then this Hahn space, this is just a standard multiplicity 1 result for generic representations. This is just a space of Whittaker functionals, and this is one-dimensional. However, if pi is generic, then this previous result that we commented on, we also have the dimension 1 of this period, which is exactly what we have here. So there's sort of a squeeze situation going on here. We have dimension 1 on the left side, we have dimension 1 on the right side, and everything in between has to have dimension 1 as well. And that's the period ping pong. Once you have period ping pong, you can get Howe duality relatively easily. And let's see how this leads to the duality result. Here's the proposition we want to prove. Notice that we're so far only mentioning generic representations, and I'll explain that in a moment. But if pi is a tempered and generic representation, then the theta lift cannot have 2 irreducible tempered quotients. Now, since you know that tempered goes to tempered, this really tells you that the quotient that theta of pi can have at most 1 quotient. Also, we already proved, we already mentioned the decomposition of theta of pi into the cuspidal and the non-cuspidal part. This shows you that the cuspidal part, since it's semi-simple, is either 0 or irreducible. And that also gives you the full finite length result, because the Jacquet modules give us the finite length of the non-cuspidal part, and here we see that this is either 0 or irreducible. So that's how we get finite length. So how do I prove this? Assume the opposite. Assume that theta of pi has 2 irreducible quotients, which are tempered. Then you use period ping pong to deduce that these 3 Hahn spaces are one-dimensional? Well, first you use period ping pong for pi and tau 1. Now I have to scroll back, which is not optimal, but let's see. We have this Shalaika period of tau, and we have the Shalaika period of theta pi. Both of these appear here. So Shalaika period of, okay, we use the theorem for contragradients, but it's the same thing. We know that this is one-dimensional and that this here is one-dimensional. So we have that these two guys are one-dimensional. But you can use the ping pong for pi and tau too. So the situation is completely symmetric. So the theorem also gives you one-dimensionality of this last period. So all of these three guys are one-dimensional. But then on the other hand, this direct sum is a quotient of theta of pi's, and it simply leads to a contradiction because this Hom space involving the theta lift has to include Hom spaces of tau 1 and tau 2. And that would imply that 1 is greater than 2, and that's a contradiction. So it is impossible.
Excuse me?
Yeah.
So in your ping pong, you don't assume that tau 1 and tau, that pi and tau are irreducible, right?
Oh, I do. I'm sorry. I do. Why? There we go. Yeah, they are irreducible here. So
then how do you use this ping pong game for tau 1 plus tau 2?
Oh, sorry. I do not use the ping pong game for tau 1 plus tau 2. I use it first for pi and tau 1. So I get the one dimension for the first two spaces. And then again, I use the ping pong for pi and tau 2. So I first use the proposition to prove that these two are one-dimensional. And then I can forget about that and prove that these two are one-dimensional as well. Does that answer the question?
So can you repeat how you derive the last inequality?
So again, I forget that I know this, and I just use the same thing. I mean, I use the same thing for pi and tau 2, because the assumption is that we have this. So I can use my ping pong to, we have pi and tau 2 appear as a quotient. I use the ping pong, and I get that this Hom space is one-dimensional. For, in this case, I use tau 2. And this is one-dimensional as well. So this gives me the one-dimensionality of the last Hom space. I simply use the same proposition twice. First, for this situation, pi leads to pi and tau 1. So I use the proposition once for this, or I should be really writing the contragradients, but okay. And the second time I use the proposition for these two guys. I use the same proposition twice.
Yeah, yes, that's clear. But then later you get the inequality that the dimension is more.
Okay. So later, once I have this, that these all are one-dimensional, then this is here. I just forget about the ping pong, and I just say, well.
Okay, fine, thank you.
Yeah. Okay, and so this leads to a contradiction. So theta pi cannot have two irreducible tempered quotients, and this is one important chunk of the Howe duality that we now prove. The other important chunk is the lifts in the other direction. Well, if I start with a tempered representation of G prime, then this ping pong can help me prove that the theta lift cannot have two tempered but generic quotients. And the proof is the same, except I use a different part of ping pong. So I assume that pi 1 and pi 2 are tempered then generic, again appearing as a quotient. Then the same thing, that I have the dimension of this co-invariant space has to be at least 2. But we actually know that the dimension of the co-invariant space is 1. How do we know that? Let's go back to the ping pong. And this time I use this part of the ping pong I haven't used in the previous proposition. So in the previous proposition, I used this guy and this guy. And now I use the fact that this thing has to be one-dimensional to prove that this Howe space is one-dimensional and therefore arrive at a similar contradiction. So really what this gives us is Howe duality for generic tempered representations. And I haven't said anything about non-generic representations because we cannot use this ping pong for non-generic representations. For non-generic representations, we have to use, there is a different period ping pong that we can use, but this maybe extends, this is beyond maybe the scope of this talk. So I should probably talk about that and next time if we have a chance. Maybe as a closing remark, so this is how you get a hold on the Howe duality. As a closing remark, I would just like to say a couple of words on how and why we're interested in this correspondence in the first place. And sort of this is a project that we're just starting, but it has been sort of a long-standing, ongoing project of Wita Gunn and Nadia Gurevich to construct the non-tempered A packets of G, both local and G2, of both local and global. And this correspondence is going to help construct the, well, at least we hope, is going to help construct the last missing family of the non-tempered A packets of G2. So that's kind of why it's exciting to study this local correspondence, because ultimately we're trying to use it in a global type of result, the construction of A packets. But this is again a topic for some other time, and now would be probably a good time for me to stop and take questions. So thanks very much.
Okay, thank you. Questions, please.
Do you expect that the same strategy will lead for other exceptional dual pairs? And how do you find the analog of Shalaika's group in?
This is a great question, and I actually must say I'm not sure if this carries over to other. So up until this ping pong part, everything we do is sort of almost uniform for every. The approach looks the same for every other exceptional group, but at this point here, it felt like certain things had to align for us to be able to use this ping pong. Primarily the reason that this works here is that this is just a quasi-split version of the correspondence, the split correspondence in E6, which is kind of simple. And Wita and Gordan already studied that, and sort of we knew what to expect in this case. But I must admit, I'm not sure what happens in other quasi-split or even split cases that are not this simple, because as you said, it's not clear which of these subgroups and periods come into play.
So thank you for your answer. But can you specify this ping pong game? When do you know it's over? I mean, you start with a representation and compute certain model on it, and you want to arrive to, maybe you can bring back to what, this, and you want to arrive to this final line home G of certain coinvariance of pi of minimal representations to pi. Is that what you are? You said that this ping pong is relatively short, might be longer.
Yes. So it's not. This is sort of a general situation. You can sort of start from one period and try and bring it to the other group and whatnot. What happens here is exactly as you say, the period ping pong stops. I start from a period of pi, and I stop when I get this type of situation here. The reason this works is the reason this is short, I should say, is that we have only we have only this step that that is involved here, and as soon as we understand this, I guess Howe space is when we can start. So I really haven't told you about the missing information here is the structure of this co-invariant space, and this turns out to be introduced from another subgroup, the Fourier-Jacobi subgroup of G2. And the reason we're able to analyze this space successfully is what makes this ping pong stop. But if this turned out to be some more complicated representation, in which case we wouldn't maybe have this result, we would, or wouldn't be able to prove this result, we would have to maybe keep doing that type of thing.
So you want to end up with one-dimensional space?
Yes, I want some sandwich thing to happen. So I do want to end up with a one-dimensional space.
Okay, thank you.
I just want to ask really quickly. I mean, of course, I don't work on the classical, on the exceptional group correspondence, but when you form your capital or your big theta, I guess something you said before seems to indicate that, in contrast to the classical case where big theta has unique irreducible quotient and some kind of an extension in general, you would say at some point that it was a direct sum of a cuspidal part and a non-cuspidal part, big theta of pi. Did you say that earlier? I think you did somewhere.
Yes. So but that's
right.
That's just a general thing that we can do for any representation, right? I have
yes, Russ, but what I'm saying is that in the classical case, the big theta has a unique irreducible quotient, so you'd never see it as a direct sum of two pieces, right?
Yeah,
because
sure.
Then here you have two quotients, and in the classical case, one of those would have to be 0 because you'd have a unique irreducible quotient, assuming you get all these finite length.
Absolutely, and this is exactly.
And in this situation, yeah. Go ahead.
Sorry. Yeah, this is exactly what happens here. It turns out we just. A priori, we don't know that this happens, so we have to assume that we might get two parts. But then this result at the end, where is it? So yeah, the cuspidal part is either 0 or irreducible, and it turns out when it is irreducible, the other non-cuspidal part does not appear. So we do.
Right. Okay, that's what I was checking.
Yeah.
Okay, that was what I was checking, because I got the impression that maybe there are situations, and of course I think for finite groups there are situations where this big theta has got different pieces and doesn't actually match what happens for local fields. And so I was wondering whether anything funny happened in the exceptional case.
Yeah, so in this case,
it's as expected. It's as expected, but not yet on that slide. Yeah.
Right.
Yeah. Okay.
Yeah. Is it possible to download these wonderful slides?
Well, thank you. I will. I think Dima sent them to the chat. I can. There we go.
It's possible to resend them again. Yeah. Thank you very much.
Okay. Also, yes. If after the talk you would remember that you wanted to discuss anything or anything else, I would be very happy to talk about anything related to this.
Okay, thank you.
Any further questions? Then thank you again.
Thank you much. Thank you very much for having me.
We continue with the seminar in 2 weeks. Everyone is welcome. So we will have seminar every 2 weeks this semester. And the next speaker is Howe, and he will talk about the number of irreducible representations in the cuspidal automorphic spectrum.
Okay, great seeing everybody. Hope to see everyone in person at some point, hopefully.
Sure, you're welcome to visit Weizmann.
Okay, when the travel situation normalizes, I hope to. I have big travel plans for this spring, COVID permitting, so who knows?
Yeah. So the current numbers in Israel are so high that probably by the spring everyone will be immune.
Yeah.
Because most of us will already have it.
Yeah, it seems to be what the US is counting on as well. I'm